Okay, so we're following up on the Prime Sieve program that we did using array lists, and I want to just do one thing to try to make it more efficient. And let me see if I can explain again why what we're doing is kind of inefficient. Because we're testing all the numbers times all the other numbers. So 2 times 3, 2 times 4, 2 times 5, 2 times 6, 2 times 7. As we find a number, we cross it off our list because it can't be prime because it has two factors. But then when we go up our list of numbers, um, we don't have to test the ones that we already crossed off. Um, we also don't have to test any number less than the ones we've done already because we don't have to test 3 times 2 if we already did 2 times 3, right? So let's see if we can make this a little more efficient. And I'm gonna measure the efficiency just by kind of counting seconds and making note of it. So for Project Euler number 10, we need the primes up to 2 million. I'm just going to calculate the primes up to 2 million and sort of count blinks. 1, 2, oh, 3, like 4 blinks of the cursor. That's pretty fast. Let's see if we can make it even faster. So here's our loop where we're marking off our prime numbers. We start at 2. We go up to the maximum. Do we really have to do that? We do. Do we? As we go through our numbers, multiplying them by one another, everything between half the maximum and the maximum is going to be covered by some lower number. So I think we only need to go up to maximum over 2 for our first number. And then, and I hope I don't get an error for that not being an integer. I guess we'll see. And then for our second number, we don't have to start until, we don't have to start all the way back at 2. We just start on the current number in our outer loop. And we don't have to go up to half the maximum. We only have to go up to the maximum divided by that number because, again, everything else will have been covered already. Let's see if this works. Suddenly I'm doubting myself. Let's give it a number that we know the answer. Let's give it like 31. Yeah, there we go. 2, 3, 5, 7, 11, 13. Those are all the primes up to 31. So I eliminated the double multiplying, okay? And I eliminated multiplying, like if my number is 31, I don't have to be testing 20 times things because 20 times anything is bigger than 31, right? That's why I only have to go to half. Okay. So that works. The other thing, though, that I can do here is to only do this if that number is prime. The number that I'm counting it to. The first number or the second number? The first number. The second number takes care of itself. So I'm going to put an if statement in here. If what? If the current number is prime, so if primeness list, if primeness list dot get the value of the primeness of number. If primeness list get number is equal to true, then go ahead and check. If it's not, then there's no need to do this step because we would have found that all those multiples are not prime anyway. I'm doing a really bad job of explaining this. Say we're on number equals 4, right? There's no need to check number equals 4 because all the multiples of 4 already got crossed off when we did 2. Okay? Suppose number equals 9. There's no reason to look at multiples of 9 because all the multiples of 9 got crossed out when we did multiples of 3. So only do this step if the current prime number hasn't been marked off yet. The current number in the list hasn't been marked off yet. Is that going to work? It better work after all that bad explaining. Let's do it again with a number we know like 31. 31. Still works. Okay? You can't tell that anything different has happened, but when it did its multiplying, it didn't check 4 and it didn't check 8 and it didn't check 9 and it didn't check 10 because all of those were already crossed off when we checked 2 and 3 and 5. Okay? So it still works. Now, I can ask it, find all the primes up to 2 million, and it should be a little faster. 2, 1, 2, 3, 4, 5, 6 zeros. Was it noticeably faster? Not really. Still about 4 or 5 ticks of the blinking cursor. Okay. But it makes me happier to know that whatever's going on in the background is faster than it was before. Let's remind ourselves what Project Euler number 10 is. Find the sum of all the primes below 2 million. I'm going to go ahead and change my comment at the beginning. This program solves Project Euler number 10, which asks us to find the sum of all the primes below 2 million. And I was thinking about this in the last video, and I think I said, well, we'll just do this, right? Then we've got a list of all the primes, and then we'll go through it and we'll add them all up. If you, in between the last video and this one, look to see if Java has a built-in method for adding up the items in a list the way Python does, it really doesn't. But then I realized I don't think we have to do that, do we? I think just as we find primes, as we put them in the list, also add them to a running total. Right? So let's create a new number. Better make it a double because I'm not sure how big this number is going to be. And call it running prime sum and initialize it as 0. Sorry, not a double. Excuse me. Pardon me. A long. Doubles are to floats what longs are to ints. I just mixed them up in my head there for a second. So, a long integer, because we don't know how big this sum is going to be. It might be bigger than 2 billion. Better safe than sorry. Okay, and then let me copy that so I don't have to type it again. Where am I collecting my prime numbers in a list? I'm doing it right here. Okay, starting at 2, going up to my maximum, and if primeness list of that index is true, then add that number to my list of primes. Well, then all I have to do is, oops, pardon my scrolling. After I do that, just add that n to my running total, right? Running prime sum equals running prime sum plus n. I look for all the trues, add them to my list, add them to my total. And I don't even need, in fact, do I even need the list anymore? The list of primes? If I'm not printing them all out, I don't even need the list anymore. I'm going to take this out. All I need to do is add them to my total. So my output is now not here are all the primes. My output is just here are the sum of the first, and then we need a blank, and then maximum was our variable name, and then a blank, primes, colon, blank, close parentheses, semicolon, and system print my running prime sum. That should do it, I think. Let's see. Let's do it with something easy. Let's do it for the primes up to 6. That's not a 1 and 0, that's a 10. It just hit the edge of the screen before. Is the sum, oh, it's not the sum of the first 6 primes. It's the sum of the primes up to that's different, right? Up to maximum. So we'll do it like this. The sum of the prime up to maximum is colon. So I said up to 6. So it says the sum of the primes up to 6 is 10. Is that right? What are the primes up to 6? It's 2, 3, 5. 2 plus 3 plus 5 is 10. That works. The Project Euler is always nice and gives you an example. The sum of all the primes below 10 is 17. So let's test it with 10. Oops, where am I? I'm here. Prime of the sums up to 10 should be 17. There you go. So that means I should be able to just run it. Give it 2 million, 2, 1, 2, 3, 4, 5, 6. Look how fast that was. 1, did we need a long int after all? What is this number? Yeah, that's more than 2 billion, right? 922, yeah, it's 142 billion. So we did, I guessed right, we did need a long int, not just an int. So I should be able to just go to, oh, I'm not signed in. Go to Project Euler, sign in, 52450 is my caption. That was number 10, summation of primes. This is my answer. What's that? 149,913,828,922. Yay, got it right. Okay. So we had to do a lot in order to solve this problem. It wasn't as simple as just learning out how to find primes. We ran into the limitations of an int and had to learn about longs. We needed to save the primes in some sort of list as we found them. So we learned about array lists. And then we learned a method for finding primes more efficiently than just brute force checking every number to see if it's divisible by every other number. So now we should be able to tackle some other problems that involve primeness and prime numbers. There is one that I'm thinking of assigning for homework. It's number 3. What is the largest prime factor of the number 6? What number is that? 600,851,475,143. What is the largest prime factor of that number? Can we, with the tools that we have available to us, solve this problem? We can certainly factor that number. Right? We've got a program that does that. We might have to change it from ints to longs. but we know how to do that. We put those numbers in a list and see if they're prime. Doesn't sound too hard. Okay, we've done all the parts of this already. Maybe I'll assign this as homework. Maybe I'll use this as an example to go through some of the other things you can do with array lists. I haven't decided how much of that to do via example and how much of that to do via, here's a problem where you have to teach yourself stuff about array lists. So we'll decide that in between now and the next couple of videos.